Welcome to our VR Developer Video 3. In this video, we're going to be using our VR app as a window to our actual database and using the places that we click on our VR surfaces as a way to query data from CSV or JSON files that contain XYZ coordinates. These are UTM coordinates that are paired with Z values that represent some sort of real-world value that we want to show on our model, whether that be elevation or oil or gas production values. I'll throw it over to Nineveh, who will introduce what we're doing in this video.
So today we'll be learning how to use geological data in VR. So we'll be exploring how to get depth data from locations on Ontario's Precambrian layer using our CSV file. And we're going to organize the data into a Quadtree data structure. We are using data collected by the OGSR Library, and we will also be learning how to access well data from a GeoJSON file, and that data is also from our library. So to get started, we're going to look at our files and how we organize the data. We decided on using raw data in these formats as opposed to organizing everything into a database using products like SQLite, as we wanted to avoid using third-party plugins. So our CSV file is just a simple XYZ file, as you can see. And for our JSON file, we took GeoJSON files from QGIS. So here's a GeoJSON file that we exported from QGIS, and I just resaved it as a JSON file.
So this JSON file is just a regular GeoJSON file saved out of QGIS. We've just changed the extension to say JSON, otherwise Unity doesn't like it.
Yeah, we'll just say it doesn't work with the JSON utility class from Unity. So for our scene, we're going to continue where we left off in video 2 and work with the same scene to allow the laser to click on the layer and populate the nearest depth point, as well as display that information on the canvas we created last time. So first off, I'm going to import the necessary objects that we're going to need for our scene. Let's go through what we just added. So I added a couple of prefab game objects that I made quickly, as well as a material. I made a little ring that will represent the click location when we click our laser. We also have a cylinder object, which will represent a pin where the depth point will be. And we just have a little material to add some decoration to our game objects. We also have imported our JSON file as well as our CSV file. And all these scripts that you see are what we're going to use for the scene and also to build our Quadtree data structure. And we'll go through those in a bit. So let's set up our scene now. So we're going to place the cylinder and the ring object into our scene. And we're going to put them off to the side. They just have to exist in our scene for us to populate them later. So I'm just changing a couple of aesthetic things, so the scaling and adding materials and that sort. Both of these game objects are also tagged accordingly, since we're going to need to grab their tags in the script. So I have the ring as click arrow and the cylinder as depth cylinder. So we had our game object that held our detect laser on layer script from our last video, and we're just going to delete that because we don't need it for this scene right now. And we're going to add our Quadtree loader script. So for the file path field, we're going to link our CSV file. So I'm just dragging that in. And for the top right X, top right Z, and the bottom left X, bottom left Z, we're going to approximate a rectangle using a few game objects that will cover the whole layer. So I'm just going to place 2 cylinders at the top right corner of the layer and the bottom left corner of the layer, and the script that we have will take those coordinates from the game objects and create a rectangle around the layer. It should encompass the whole layer.
So you're using these objects to make a bounding box around the geometry that we want to search?
Yeah, so we're gonna take their positions and just put them into our fields later on. The top right X, top right Z fields in our code. They're just approximate values. So we're going to take the transform x and z values from these cylinders and put them into the fields in the Quadtree loader script in the inspector window. So you're just going to look at the values like where they are placed inside the scene and just copy those values in. And we don't need that extra cylinder, so I just got rid of it. All right, so that's all you really need for this scene. You can build it, and we should be able to detect the laser on the layer and click, and the code will locate the closest depth point and place a cylinder down. The information about the depth point will be displayed on the canvas that we tagged and built in our last video. So we can go into explaining the code that we use to build these functionalities.
So the first class we're going to be looking at here is the Quadtree class, and this is implementing our Quadtree data structure. So just to explain a little bit about that, a Quadtree is a data structure that will help us with our sorting and searching algorithm to find the closest coordinate to any coordinate that we plot on the geological layer. For the amount of coordinates we have in our file, a search which needed to check each individual point in the file was not practical. So that's why we implemented this Quadtree, which brought our search time down considerably. So the Quadtree works by recursively subdividing the entire area of the layer into quadrants and inserting the current point into the appropriate quadrant based on the top right and bottom left boundaries of that quadrant. So this way, when we go to search for the closest point to a given point, it's a lot faster to narrow down our search since we know which quadrant we should be searching in. So for each subdivision of the layer, the volume of points to search is reduced to a quarter of the original size since we're using quadrants. There are also a lot of great resources on Quadtrees to learn more about them, but for our purposes, I'll just be briefly explaining how each function in this class works. So first, we implemented a class constructor, which will initialize a new tree based on the top right and bottom left boundaries that we pass to it to ensure that the tree includes all possible points on the layer. So here we have a helper function called inBoundary to determine if a given point exists within the boundaries of a quadrant, which we will use to help us out later on. And then we have this insert function, which takes a node which we have built, and we'll talk about the node class after this. And it inserts it into the Quadtree at the correct position. So this is a recursive function which determines, based on the boundaries of the current quadrant, whether the coordinates of the node belong in the top left, bottom right, bottom left, or bottom right section of that quadrant. Once this is determined, the function is called again, and the selected quadrant is further subdivided into 4 sections, with the boundaries recomputed to reflect this. So the function ends once we have reached the smallest subquadrant possible to insert the node, and then we insert it at this position in the tree. Our search function works in roughly the same way, but instead of subdividing the tree to insert a point, we divide the tree to search for where a given point should exist, and then we can return the closest point that we find. And we also have this function called neighbor search, because sometimes we'll arrive at the smallest subquadrant that a point should exist in, and there are no points there to return. And this happens because we're looking for closest points and not exact points. So we solve this problem by simply reversing our search by 1 subdivision level and checking each neighboring quadrant until we find one that's not empty to return the closest point. So now that we've discussed how our tree structure works, we can read our coordinate data from a CSV file and insert each point into the Quadtree. So we have a function here called buildTree, which takes our CSV file as a text asset to read from. And we already attached this file to the script in the inspector earlier, as we showed. So now we can actually access the data. So this function works by reading in each line of the CSV file into an array by splitting it on the new line character. We can then check to make sure the array and its indices are not empty before we use it so that we don't get any unexpected errors. And we will now call our build node function with the current CSV line, which will create a new node from the data contained in the line. After this, we'll insert the node into the tree, but let's go back and talk about the build node function first. So this function will split the current line on a comma into its UTM coordinates and their associated depth value, and then it saves each of these into their own variable. So we'll need to convert our real-world UTM coordinates into Unity space coordinates, which will correspond to locations on our model layer. So the model we're using has a 1-to-1 model to real-life scale, and we've just translated the location of the coordinates and scaled the size of each down by a factor of 0.0001. So we must now undo these transformations with the equations shown in the script to to plot the points correctly on the layer in Unity. We can now create a new Quadtree point based on the converted coordinates and use this newly created point and the associated depth value to create a node to be inserted in the tree. So we have two classes to help with this, which are Quadtree point and Quadtree node, and they are responsible for holding the data in our tree. So this Quadtree node class creates new node objects for the tree, and each node holds a point as well as a data object, which in our case is going to be the depth value from that point on the layer. And then our Quadtree point class will create new point objects, which will hold a set of X and Z coordinates in Unity space. And these points are then stored in each node of the tree, as we've seen. And then finally, we have our Quadtree loader script. So this is the final element to bring all this functionality together into our scene. So this script will allow us to plot a point at a raycast location on our layer and return the closest point that was found in the CSV file we are reading from by spawning a cylinder game object in that location and printing out the depth value associated with that point. And the height of the cylinder we spawn will also have a scale that corresponds to the depth point at that location, so we can better visualize the different depths of the layer. So we first need to make sure at the top of our script that we are using the extra namespaces system.io, unityengine.ui, and system.runtime.serialization. And just go ahead and include these in all the other scripts as well. Next, we will declare some variables for our class. So we have our Quadtree objects, the boundaries of the layer, which we set earlier in the inspector, as well as point objects to store them in. We have our text asset CSV file, which we also set in the inspector. We have our canvas text, the layer, the cylinder, and then the depth arrow game objects, and some width and height properties to associate with our cylinder. And then we also have a variable to store our controller button clicks. So in our start function, we will declare an instance of the class, and we'll also save all of the game objects we need into their associated variables by accessing their tags in the scene, which we showed us tagging them earlier. And we will also enable our canvas object so that we can use it later. And we will save the X and Z width of our original cylinder objects to use in transforming the scale of our spawned objects later on. Next, we want to create a new Quadtree, passing in the top, right, and bottom left points that we created for our layer, and we will call the build tree function, passing in the CSV text asset, which we have already seen will build the tree for us. So next, we'll move down to our update function. The code used here was shown in our previous video on raycasting, so I won't explain it in depth, but we are basically continuously checking for raycasts from our controller, and then we're going to call the clicked function whenever the layer is hit. So in the clicked function, we are now spawning a new depth arrow game object at our raycast location just to mark the point that we've hit on the layer. And we talked in depth about the process of spawning a new game object in our last video as well, so go check that out for more detail on how that works. But once our new game object has been spawned, we will pass this object along with our raycast hit to our build new tree function. So the build new tree function will handle the bulk of our work in the script. So it's going to search for the closest point in the Quadtree to our new spawned game object, and then it's going to plot this point and print out its depth data. So we refer to our game object as a cylinder here, but just to be clear, it's still the same depth arrow object that we spawned in the last function. So we're going to start by getting the local X and Z coordinates of the object relative to the layer, and then creating a new point object with these and calling our Quadtree search function to find the closest point that exists to this one in our tree. An if statement ensures no error occurs if a closest point was not found, but if it was found, we can move on to the else statement. So we can now take the node containing the closest point that we found and save its X and Z coordinates and depth value. And we'll plot a new game object at the location of these X and Z coordinates, again, relative to the layer, to visualize this point. And we'll also adjust its height by applying a function to scale it taller or shorter based on the depth value. We will now convert the coordinates back to UTM with the same scale we used earlier, and we'll now be able to print out the coordinates in Unity space as well as their original UTM values. And we will print this all to the canvas along with the depth value. So we can now go back into our scene and see how this all comes together.
The viewer might be wondering why we're going to scale the cylinder based on the Z value, since in this case the Z value is just the depth to the layer, which you can clearly see on the layer itself. But other data that we bring in here, like oil, gas, and water, will have Z values which represent the volume of those fluids that are pumped from a well. And so we can scale that cylinder based on those volume data, and then you can compare visually which well has produced more of those fluids.
So we're just building our scene onto our headset. Make sure we're connected with Oculus Link. Okay, so now we have an alternate scene that I've set up really quickly just to show you guys how we read data from JSON files instead of CSV files. So I just set up a quick scene with just the regular main camera that Unity gives you in a scene with the directional light, and I created a quick canvas with a panel and a text object. So in an empty game object, I'm going to add the Quadtree well loader script. And in the file path, I'm going to link our JSON file. And since this data is from a Cambrian layer, so I've already figured out the top and bottom coordinates for that, so I'm just going to input those in. It's similar to how we did it in the CSV example. It's the exact same method. I just got the work done ahead of time. All right, so that's all we have to do to set up our scene. So now we can go through the scripts. So I'm just going to open up all the scripts that are used in this scene.
So we're going to be using the same Quadtree structure to search and sort through the JSON file that we used for the CSV earlier. So this class is almost identical, aside from the function that we'll use to read in our data from the file to build the tree. So the process of reading from a JSON file is slightly more complicated than that of reading from a CSV. And this is because we'll need to save each JSON key to its own object or a class in C#, following the nested structure of the file. So each key needs to be stored exactly how it's spelled in the JSON file, case sensitive, and the data types must match as well. So following the structure of our file, we have this class called features, which represents the array in the JSON file, which wraps all of our wells. So our features class thus holds an array of well objects. We then have a class to hold each well object along with its attributes, and it has a type, properties, and geometry. And since the properties and geometry attributes both have nested keys within them, they have to have their own classes as well to hold the data that they store. So the properties class stores the license and depth value of the well, and the geometry class holds the geometry type and a set of coordinates of the well location. So the coordinates we're using here are the same as when we read the CSV file, so they're going to be UTM coordinates that we just converted into Unity space. So when we read from our JSON file in the build tree function, we use the JSON utility function called from JSON, and we need to read our JSON file into the features object. So this process will automatically recognize the naming of each well property and save its attributes into an object of the associated class, following the class format that we just discussed. So for each well object in the array of wells stored in features, we will build a node for this object and insert it into the tree. And then in the build node function, we will take the well object and store all of the properties we need in a tree node. So we save the license number, the Unity converted coordinates, and the depth value. And then we create a point object and a node object as we did with our CSV file. Here, the node will just contain different information. And here's what the node looks like to store our well data. We're also using the same Quadtree point class from before, since we're still working with the same UTM coordinates.
So our Quadtree well loader is very similar to our Quadtree loader class. I'm just using a simple canvas instead of all of our VR components and inputting my own point into the search to pull up a value. And you can see it found the correct license, and we're displaying the information on the canvas there. So now we can test out the code that we have to read from the JSON file. So here I am in the scene. We can see our canvas displayed in front of me, and I'm standing on the Precambrian layer. So when I click the hand trigger on my right-hand controller, I'm pointing the laser at the layer surface. When I click the trigger, it should place a ring where I have clicked on the layer, so that's the detection location, and the cylinder should be placed in the location of the closest depth point value. And we should see the information of the closest depth point value on the canvas in front of me. So you can see them in both UTM and Unity coordinates.
And that's it, right? That's how to get your real world data from your tabular databases into your VR and query it by clicking on your actual geological surfaces. Now that we can click the surface to get tabular data, we can use this to search all kinds of databases, right? So elevation thickness, oil, gas, water production, salt thicknesses, all kinds of data can be revealed through the VR app by using this query.
So next time you can look forward to us implementing 360 video footage in our VR headset.
Yeah, we'll have a look at some of the real world locations we're bringing into the VR app with our GoPro Fusion and sorting out some of the difficulties with bringing in 360 video and spatial audio.